Okay, I think I'm recording, and this is 3.7 optimization problems. I had to put my pay-per-view on so that we can do some of these problems and see how we do. 3.7 on optimization problems. They're word problems, and it just gives some of them get pretty complicated, but some of them, I'm going to be showing you my favorite types here, but some of them are okay. I mean, you can kind of set them up. So here's kind of the story. You read through the problem, you list what knowns and unknowns you can find, and the big question is, what do you want to optimize? So if they're not talking about something they would like to optimize, then you know this is not an optimization problem. Sometimes it's helpful to draw a picture and label things, and then you want to come up with an equation, and it's with two variables in it. And it would be lovely if you could have what you would want to optimize on this side of the equation, and then yada yada on the other side of the equation, whatever you have to have in one variable. That'd be lovely. Then what you do is you take the derivative with respect to this variable that you have, find the critical points or critical numbers, and check the critical points and your endpoints for the absolute min or the absolute max. And then you want to prove that you've have found an absolute min or an absolute max, because a lot of times you just have one value and you don't even know if it's a min or a max, but you want to prove that it's a min or a max. I like to use the second derivative test for that because it kind of gives us an opportunity to get to use it. And then answer the question asked. You can also use the first derivative test. And I know there's at least one problem in the homework, if you do the homework, that asks you to find the maximum. You go through all the trouble of finding it. You say, okay, that's my answer, and really what you found was the minimum. So so it's good that you check it out and make sure that it is. Then so I was making this video. This is the first problem, number 15, that I have. And I said, oh, I wish that I would have had an easier one first. So here is an easier one. And this is coming off of, that we're going to start with. So this is a bonus example. It's coming off of quiz 7. Number 15. No, number 12. Sorry, the other one's number 15 out of the textbook. This is number 12 on quiz 7. It says an enclosure will be built as depicted. So they're going to make an enclosure like this out of some fencing. What dimensions for X and Y will maximize the area? Remember to prove that you have found a maximum. Give the exact value and do not round. Okay. So they want to maximize the area. And so I'm looking at this this enclosure that they're gonna build, and they want to maximize the area of this enclosure. So, well, what is the area of this enclosure? So, the area is X times Y. So, of that enclosure, I mean, it's kind of like a 3-pin situation, is what you got there, and you're trying to maximize. You're trying to make those 3 pins as big as possible, and so you kind of, when you go back to what I was going to try to do, well, it said that I might want to list some knowns and unknowns. So X is the side of the pin, and I'm going to have 4 of those X's to make this pin. And Y is the other side of this pin. I'm thinking it's a pin, this enclosure. I'm going to have 2 of those, right? So I'm kind of thinking about what are the, read the problem. What do you want to optimize? I read right away that I wanted to optimize the area. I want the max area. So I want to maximize that area. And the picture was already drawn from me to tell me what they wanted the enclosure to look like. Right. Okay. And then I'm trying to write an equation using only 2 variables. And you notice that, Oh, is that focused? It is. That, well, I have three variables. So I do have what I would like to optimize on this side, but on this side I have two variables, and I wanted to have just one variable on that side. But I have uh, some things that maybe I haven't used yet, some information, right? That so let me read through the problem and figure out that information that I haven't used. So it says an enclosure will be built as depicted with 50 feet of fencing. I don't even think I read that the first time. I just went right over it, right? And so that's what is that that they're this is the fencing that they're going to be building here and here and here and here and here, and they have 50 feet of it. And so they're going to have with their fencing, they're going to have to make four um, X's, right? So it's kind of like perimeter here, and two Y's here and here to be 50 feet. That's what I know is going to happen. So now, um, what I would like to do is I would like to get just one variable on this side, and I can use this equation here and I can solve for either x or for y. It doesn't matter. I'm kind of noticing that if I solve for y, because 2 goes evenly into 4, then I won't have any fractions still to deal with. As if I go the other way, I'll have a fraction to deal with, but it's okay. And so I'm thinking about solving this for y. So to solve this for y, I'm going to take away 4x from both sides. So taking away 4x, and then, so that's going to be 2y equals 50 minus 4x. Then I'm going to divide by 2, all of the pieces. So I get y equals 25 minus 2x. And now I'm going to plug that in right here where I see y, 25 minus 2x. So this is going to become the area equals x times, and when you substitute, parentheses are implied. So I'm going to put the parentheses there, 25 minus 2x. And the parentheses remind me that I'm supposed to distribute. And actually, if I distribute and I hadn't written those parentheses, then I shouldn't have been distributing, right? So if I had written it wrong, I'll use this paper here so I don't get it written wrong on my paper. But if I had written this, this is the kind of thing I see. That doesn't mean distribute. That means 25x minus 2x, which is 23x. And so without the parentheses, and then you go and distribute, well, you're you need the parentheses to tell you distribute. And so I know people don't like to write parentheses. I don't know why. I guess maybe I was like that too. Okay, you know, I don't know. When I was your age, I didn't like to write parentheses. Is that what you're saying? Okay, so here we go. Now I have what I would like to maximize on one side. I have one variable on the other side. I am the next thing to do after you get that done, right? So here, writing the equation using only two variables. What you want to optimize on one side would be lovely if you could get it, and on the other side, one variable. I have that. Now find the derivative with respect to x, since that's what I have. That's what I have going here. So I'm going to find the derivative with respect to x. Now I could use the product rule, but it would be better since I can multiply, just to multiply first and not use the product rule. So that's what I'm going to do. So even though I was on find the derivative, I decided, so this is going to be 25x, and then x times minus 2x is minus 2x squared. And so now I'm going to find the derivative. So the optimization problems are different than the related rate problems, because in the related rate problems, you find the derivative with respect to time. But in the optimization problem, you find the derivative with respect to whatever variable you got going here. So I'm actually going to be finding here dA dx. And it's okay to write that if you want it as I'm going to write it as a prime like that. And then over here, the derivative of 25x is 25. And the derivative of this is minus 4x. Okay, so now I have found the derivative, and it says to find the critical values. So how there are critical points, and how you find the critical numbers or the critical points is you set this derivative equal to 0, right? You want to know when a prime equals 0 or when a prime is undefined. So a prime, I was writing a prime. I don't think this eraser is really an eraser on that pencil. I don't think this, erasers get old. And that eraser there should just go in the trash. I wonder if you can revise them. If you can revive, or not revise, revive. If you can revive an eraser, let me know. This is a polynomial, so it's not ever undefined. So I'll put nope. But I just wanted you to know that, hey, the critical value could have come there. And so I'm going to solve this. I'm going to add 4x to both sides. So this is 25 equals 4x. I'm going to divide by 4. So I get for x, 25 over 4 equals x. Okay. So then what I would like to do, so this is my critical value. I'm going to write that too. So this is a critical number, critical point, critical value. I have that, right? And I want to also like to check the endpoints. And some of these problems do have endpoints, and some of them don't. And this one doesn't have endpoints that make sense, because I could make x as small as possible. So if I did that, that would mean that x would maybe be 0, and I would be using all my fencing to make two parallel lines, right? That were so close together. Well, I'm not going to have any goats be able to fit in there. I mean, you know what I mean? If I made x 0, then I'd have two parallel fences, very long parallel fences, and very, very close together. I wouldn't even be able to grow a garden in there or have any chickens or anything. So, anyway, so that's not gonna work out. If I allowed x to get as big as possible, then that would mean I would be using all of my fencing to make these, and y would become 0. And so I'd have the same thing, except for I'd have 4 parallel fences is what I'd have going. So the endpoints don't make sense on this one, because that's what the next thing that I would do is I want to check the critical numbers and the endpoints. So the next thing is to check for the max, right? Because they said to maximize it. So we want to check the critical numbers and the endpoints for the max. But on this particular one, I don't have any endpoints to check. There are problems in the book, not these pen problems necessarily, or the volume problems necessarily, the pen problems and the volume problems don't usually have endpoints that make sense. So anyway, I only have this critical number, and that's what I was saying to you, why you want to prove that it is a maximum somehow, because if I go and I plug it in and I find the area, which I certainly can do, and I can then find y as well, right? So I can come right here and I can plug it in and I can find the area, and I can plug it in right here and I can find y. So depending on what they've asked me to find. But how do I know that that's a maximum area and not a minimum area? This critical number didn't come telling me what it was. I just know that it's could be a max or a min. And so what I want to do is I want to prove that it is a maximum, and then I'll go and find all the things about it. And I suggested that you could use the second derivative test. So right here I have the first derivative. So if I take the second derivative, and I have a place over here, prove that you have a maximum. So if I take the second derivative, because I'm going to use the second derivative test, well, then the derivative of the derivative is the second derivative, and then the derivative of 25 is 0, and the derivative of this is minus 4. And remember what and I want to plug in, and I'm saying when x equals 25 over 4, and I know there's no x in this one, so I don't get to even plug that in. And so that would, when x is 25 over 4, my second derivative is negative, which means that it's always concave down. So this was a critical value, right? X was a critical value on something that's always concave down. Because the second derivative is negative, that means it's concave down. And it's concave down for all values of x, not just my particular value of x, but that's why I just wanted you to know I would plug in my particular value of x if it had a variable in it. But this one's always concave down. And so what that means is, and I've kind of drawn a picture here, it's a critical value. And so 25 over 4 is, so thus it's a max. Thus. So I say prove lightly here. I'm going to go more with verify that it's a max, and I'm using the second derivative test to verify that it's a max. So now, some of these problems ask you to find the area, and some of these ask you these pin problems, I call them, ask you to find the dimensions. This one asked me to find the dimensions. So I want to find x and I want to find y. So I have found x here at 25 over 4, and I'm going to find y. And how I find y is back in that equation. Y equals 25 minus 2x. Well, x was 25 over 4. So y equals, and I'm just going to get my calculator out. So y equals 25 minus 2 times 25 over 4. 25 over 2. That's 12 and a half, right? 12.5. 25 over 4. Kind of early this morning, I don't know. It's 6.25. So I'm going to go ahead and write this as 6.25. Just because I like when I'm measuring. And this was in feet, and 12 and a half feet. So that's going to make the biggest area possible there. If you just kind of wanted to investigate that just for a second, just to see, right? So what area does that make? Well, if you multiply those together, that'll give you the area that my pins are made with, 6.25 times 12.5. And the area that is making is 78.125. So the area that I've currently have is 78.125. I don't have room to write feet squared, but I'm going to put it underneath it, feet squared. And if you were just wondering, well, this is supposed to be the very maximum area that I could get with 50 feet of fencing. And so let's just try something else just to see. And so let's say that instead x was 5. So if x was 5, and I'm just doing this just to show you that, yeah, that was bigger than everything else. So that would be 5 here, 5 here, 5 here, 5 here, which altogether that would be 20, right? 4 times 5. Here it is right here. And then 25 minus that, right, to give us what y is. That's what we were wanting to do. I guess I'm because I've divided this formula by 2 to solve for y instead of having both y's here, you know. So anyway, so let's figure out what y would be for this situation, and we'll go back and make sure that it's using 50 feet here. So y would be 25 minus 2 times x, which was 5. And so that would be 25 take away 10, which is 15. And then I'm just going to make sure that's using 50 feet of my fencing. So 15 here, 15 here, that's 30. 5 here, 5 here, that's 40. 5 and 5, that's 50 altogether. So I've used 50 feet of my fencing, and I've got this pin that is 5 by 15. And the area for this situation would be 5 times 15. The area would be 75 feet squared. And you notice that's not quite as big as this pin here, because what I have found is the maximum pin. So if I use my fencing in this manner, I will have the biggest pin possible. And so this was just another pin. I'm even going to erase it off my paper. This was just another pin to show you that other pins that I just come up with are not quite as big. So every pin that I come up with will not be quite as big. So if I say, well, let X be 7, then I can go find Y and I can get a pin situation, but the area will not be as big. This is the biggest area. Had they asked me for the largest area, because some of the problems do, then this would have been the answer. And the area is 78.125. So mostly they don't ask you for the dimensions and the area. They ask you for one or the other. This one asked me for the dimensions, so that's what I'm giving there. And in fact, I'm going to erase this off here too because it wasn't asked for. But I was just investigating with you a little bit what I found. Now we're going to go do the problem on the notes, which is number 15. That was just a little freebie, doing one from the quiz. Reminds me I have to write the review. Okay, a farmer wants a rectangular plot of wants to fence. I was missing that part. A farmer wants to fence. I think that this word wasn't supposed to be there. I think I must have mistyped that. A rectangular plot of land adjacent to the north wall of his barn. No fencing is needed along the barn, and fencing along the west side of the plot is shared with a neighbor who will split the cost of the portion of the fence. If the fencing costs $20 per linear foot to install, and the farmer is not willing to spend more than $5,000, find the dimensions for the plot that enclose the most area. So the farmer has a barn that's going to be part of the situation. So this, we're going to say no fencing here because this is part of the barn. And he or she, didn't say, did it, is going to fence a rectangular spot here along the barn. And they said this problem came out of the book. And so I'm kind of trying to imagine. So we have the barn going here, and we have a neighbor. This was the north wall of the barn. We have a neighbor that will fence the west side. I don't know if this is the west side over here or if this is the west side over here. So I'm gonna, and I should know, but it's 4 o'clock in the morning, and so I don't know. And so right now, which like this is north. I mean, I could get my calculator out. This would be south. I could go there, and then would this be west, and that would be east, and so could I say that that's what it was? And so that's what I'm going to do. So I'm going to say over here, this is the west side, and I know that it's going to cost, what did it say? It said, so I'm trying to list out everything I know and draw a picture of what I know. So there's going to be no fencing here because this is the barn. I can't draw barns. So there's the barn. And we got the neighbor over here. And so this is, for some reason, this neighbor has said that he's going to fence part of this for us, help us pay this. Neighbor helps, helpful neighbor over here. And so let's see what it says. If the fencing costs $20 per linear foot to install, okay, so if the neighbor was going to split the cost and was willing to pay half, then would you agree that if it's $20 to fence, that this side over here is going to cost $10 per foot to fence per foot? And then this here, because we don't have the helpful neighbor here, is going to cost $20 per foot to fence. And same over here, $20 per foot. Okay, do I have everything listed out here? Oh, well, the farmer doesn't want to spend more than $5,000. And so we'll say that that's the maximum the farmer will spend is out of his own pocket. And we want to maximize the area is what we're wanting to do by keeping the cost at $5,000. So I haven't given any dimensions here at all. I haven't named something X and something Y or anything like that, but on a rectangle, that seems like a good thing to do. You could also call it W and L. It doesn't matter. Since the last one was called X and Y, I'll call this one W and L. So I'm going to call this L and I'm going to call this W. And since it's a rectangle, this side over here is also W. And so I know, and this is what I'm trying to maximize is the area is equal to W times L, or L times W. That's what they normally write, huh? But, oh well, doesn't matter. Same thing. And I want to maximize this area. And so the same thing happened in the last problem that I did is that is that I have the one variable I want to maximize on one side, that's great. And on the other side, I have two variables. And that's what's not great. I'd like to put one variable over there, then take the derivative with respect to that variable. And so I haven't used the $5,000 yet, so I'm about to use that. And so let's figure out how much it would cost to do this, right? And so the cost, it's going to cost me $10 times W on this side because W is the number of feet that this side is, and it's $10 a foot. So 10W for that side. This side is going to cost 20L because $20 per foot and it's L feet long. So 20L. And then this side is going to cost 20. I wish I had a neighbor over here. And so that's 20W. So this is what it's going to cost the farmer, right? We're not figuring out how much it's going to cost the neighbor, just this farmer. And the farmer said that wanted that cost to be $5,000. I guess he would probably be happy with less than $5,000, but we're going to say that's the absolute maximum is $5,000. And since he's wanting to get the maximum area, we'll go ahead and spend the maximum amount of money that he's willing to spend. So this is 30W, combining like terms, plus 20L. And you notice now I have another equation that I can use, and I can solve for either L or for W, and I can plug it in here, and then I will have just one variable, and that's kind of the kind of what I would like to do. That's what I want, and then I'll go figure out what are they wanting me to find. Oh, it says the dimensions. Find the dimensions. So I want to find L and W. Okay, so should I solve for L or should I solve for W? I don't think it matters here because 30 doesn't go evenly into 20 and 20 doesn't go evenly into 30. And so no matter what, I'm going to have fractions. And if I solve for W, does 30 go into 5,000 evenly? I don't know, and I guess I don't care. I'm going to solve for L because I know that 20 will divide 5,000. I think it will anyway. So I'm going to take away 30W. So this is 5,000 minus 30W equals 20L. And then I'm going to divide each piece by 20. So 5,000 divided by 20, I said it would go evenly. I thought it would go evenly. I don't know if it'll go evenly. It does go evenly. Is 250. And then 30 divided by 20, I know that it will reduce, which is 3 over 2. W equals L. And it's okay to use your calculator if you like. I could have done it in my head, but I already said it was really early. And so I want to make sure I didn't make a mistake. So right here, where I want to maximize, I have this work right here that's helping me get rid of one of the variables, and it's going to get rid of L. So I'm going to have W, and that worked out kind of good that I wrote it backwards here. And then times, just because it's nice to have your monomial written first and your binomial written second, although it could be the other way, it doesn't matter. So I'm going to put that there. And then I very much have the same problem that we had from before, except for I'm going to have this fraction in here. So when I distribute, I'm going to have A equals 250W minus 3 over 2W squared. And now I'm going to find the derivative with respect to W. If I would have solved this for W instead, then I would have had L's over here, and I would have found the derivative with respect to L. And so you could write this if you wanted as dA dW, which is A prime if you wanted to write it. Either way is okay. I usually write A prime, I have to admit, but just so you know, you're taking the derivative with respect to W. And so this is 250, right? And then the 2 comes here, and so that would be minus 3W. 3 halves times 2 is 3. And then take away 1 there, right? And then I want to find when this is I want to find the critical numbers. So that's when this is 0 and when this is undefined. But it's never undefined. Are there problems where this comes out to be undefined sometimes? And the answer is yes. And so I do try to still, nope on this one, but I still tried to check that. And so when I solve this, 250 minus 3W equals 0. So that's 250 equals 3W. So this is 250 divided by 3 equals W. That's not going to be a nice amount, but, and I'm not a person that's going to round, not a single bit. And so this is 83 and 1/3. Was this feet or yards or feet is equal to W. Okay. I just like that better, because I can kind of imagine what it's going to be, and my dad out there with a tape measure. Okay, so now I would want to check any critical numbers I have. Critical numbers and end points. And I told you that these pin problems don't often have endpoints that make sense, right? So remember, we were talking about W. So if I let W get as small as it possibly can, kind of thinking about the domain of W to get the endpoints, well, that would be 0. And then I wouldn't have a pin. And if I made W as large as possible, and that would be then using all my fencing on W going here and none across here, then so L would be going to 0, then and W would be getting as big as possible, then I wouldn't have a pin. So the endpoints a lot of times don't make sense. So I only have this one critical number right here, and I'm hoping that that critical number creates a maximum. So I do like to make sure that it's going to, verify that it's a maximum. So that I'm going to do that right here. And then I will, since I only have one critical number, right? I don't know, is that the max or the min? So I'm going to verify that it's max. Hopefully that's how you spell verify. And I'm going to use the second derivative test for this. And so when I find the second derivative, I get 0 and -3. So I get -3. There's also no place for me to plug in the W, just like there wasn't on the last problem. And so this is always concave down. And we had this critical point. 83 and 1/3 was the critical point. And so I can see that it's a max. Because if it's concave down, then it must be here at the at the top on that. Okay, so that's good. And they asked me for the dimensions, so I just need to find L, and then we'll be in business. So L equals 250 minus 3 over 2 times W. Now, it would be better if I put in the 250 over 3 for W as opposed to the improper or the mixed number, because on my well, I have that on my screen, it doesn't matter, but this is mixed numbers on the Casio. You have to hit the shift and then that fraction key in order to get the mixed number. If you try to create it yourself, it'll be times. It'll be it, and that's not what this means. This doesn't mean 83 times 1/3. It means 83 plus 1/3. And so if I try to create it without using this button right here on the Casio, it won't know that it's a mixed number. So that's why I like to use the improper fraction. So this is 25 minus 3/2. I might as well use my fraction key here. And then times, and then another fraction, 250 over 3. And I get minus 100. Oh, because I put 25 and not 250. Okay, well, I'll edit that and change that. I was like, wait a minute. Length of that better not be negative. That's crazy. So this is 125 also feet. And so the dimensions, am I going to be able to spell dimensions right? I know that they had it up there, so I could also cheat and look. The dimensions are 83 and 1/3 feet by 125 feet. And they didn't ask me to find that area. I'm going to read real carefully and make sure. So the fencing is this. Farmer only spends this much. Find the dimensions. So I'm just reading carefully. You know, what did it say? What did it ask me to find? It said find the dimensions. I found them. Okay. So this is problem 16 from your textbook. And it says, if the farmer in exercise 15, so we just did exercise 15, wants to enclose 8,000 square feet of land, what dimensions will minimize the cost of the fence? And so a little bit later, so the farmer's just making a plan, right? And so the farmer said, okay, at the very most, I'll spend $5,000. And how much, how much can I enclose? We didn't even find that area, but I would be interested to see what it is. So it would be 125 times 250 over 3, right? And so more than 10,000, almost 10,500, right? So, that's what enclosed with this $5,000 right here. And so the farmer says, what if I wanted to enclose 8,000, and this wasn't, I know that this wasn't spare feet, this was square feet of land. I knew that there was a typo on that, and I looked for it and could not find it when I was redoing these notes, and then I just found it when I was reading it really carefully. Anyway, so the farmer is now deciding, I don't need that much enclosed. What I would like is just 8,000 square feet. Well, how much would that cost me? And so so that's what he's wanting to do. He's wanting to have 8,000 square feet enclosed and be at the minimum cost. So we have this situation, because the same farmer, he's got the barn. He's got the friendly neighbor over here that's helping. And the farmer is having to pay. We called this W. We called that W. We called that L. And remember, 10 over here he's having to pay, 20 here, and 10 over here. No, 20 over here, because there's no neighbor over here. So over here, this is costing him 10 because of the neighbor. Over here, this is going to cost him, this is the cost, per foot, and this is the cost per foot, 20, and this over here is 20, is the cost per foot, $20 per foot, right? And so this time, what we're wanting to do is we're wanting to minimize the cost. So let's just write an equation that goes with the cost. So the cost would be 10 times W plus 20 times L plus 20 times W. And we actually had already done that. And in the last problem, right? And we want to minimize this cost. And we want the area here, the area, which is W times L, right? We want that to be 8,000. We want 8,000 to be equal to W times L. And so this cost that I want to minimize is 30W plus 20L, just like in the last problem. It shouldn't be different than that. Okay. But what is different is that I'm trying to minimize the cost and keep the area constant at 8,000 square feet. So just like all the other optimization problems that we do, you would love to have what you want to minimize on this side of the equation, which I do have. And then on this side of the equation over here, you would like to have one variable, but I have two. But I have this story over here that will help me get rid of one of the variables. And so solve for L or for W. And on this case, it doesn't probably matter which one that you solve for. I mean, you might figure out, because you're going to get, if you solve for W, you're going to get 8,000 over L, and I'm going to put that in here for L. Anyway, you might think, is one better than the other? And I don't think so. I don't know. Maybe maybe getting L by itself, just because 20 and 8,000 may be reduced with one another, where 30 and 8,000, they're going to multiply within each other anyway. It doesn't matter. Okay, so 8,000 divided by W equals L. So this is going to be the cost equals 30W plus 20 times L, and L is 8,000 over W. And so the cost is 30W plus 20 times 8,000. That's 16 and 4 zeros. I better do that out. Boy, I tell you what, I don't do well when I don't have enough sleep. Yeah, 16 and 4 zeros divided by W. Now I want to find the derivative. So now that's my next story. And before I go and find the derivative, I'm not going to use the quotient rule if I don't have to. I'm going to write this as W to the negative 1. So I'm going to write this as 30W plus 16 with 4 zeros, W to the negative 1. And now I'm going to find the derivative. Okay, so with respect to W, if I'd solve for L, then it would be with respect to L. And but I should have done that because I think I did W on the other one, but it doesn't it doesn't matter. And so we're going to have here the derivative with respect to W, which you could call C prime, equals 30, right? So the derivative of this, and then minus 16 with 4 zeros, W, and then take away 1. So negative 1 take away 1 is negative 2. So then I want to find the critical numbers, right? So I'm going to let C prime equal 0. And so this would be 30 minus 1, 6, 0, 0, 0, 4 zeros over W squared equals 0. And I'm going to solve this for W. So I could add this to the other side of the equation and then cross multiply because I have that variable in the denominator, and I would be creating a fraction equals a fraction. And I'm fine with you doing that. That's a good way of going. Or you can multiply everything by w squared. And don't forget that we want to know when this is undefined as well. So I'll just write that over there so I don't forget. So I'm going to multiply everything by w squared. So I'm going to be multiplying here, multiply by w squared. So this is going to be 30w squared. When I multiply this by w squared, the w squares cancel out. So minus 16 with 4 zeros equals, and then 0 times w squared, right, is 0. And now I'm noticing that I have, this is the lead term for solving my quadratic equation. I've forgotten to drink my tea. And now it's cold. And this is the last term. So I can use the square root method. So I'm going to add the 16 with 4 zeros onto the other side. So I'm going to add that there. So this is going to be 30w squared equals 16 with 4 zeros. And then I'm going to divide by 30. And I'm going to get w squared equals 16 with 3 zeros over 3. I just reduced by 10. Then I'm going to take the square root of both sides. So this is going to be w equals plus or minus. And I know that because it's a length that it really shouldn't be minus. 16 with 3 zeros now, divided by 3. And I'm going to allow my calculator to simplify that. And I'm also going to exclude the negative, but I just wanted to show you that, hey, if it had been some other application, maybe I need something negative, or if it had been a problem that I was just trying to solve without application to it. So I'm putting in there the square root of 16 with 3 zeros and a 3 in the denominator. And the calculator says that's 40 square roots of 30 over 3. And then that's approximately equal to, so S to D, 73 point, let's say 73.0, let's round to the 10th. It didn't really say where to round to, but 73.0 if I round to the 10th feet. Okay. We're math people. We want to make sure we have the exact value there so people know that that's the exact value. And when is it undefined? Well, it would be undefined. I'm looking at my second derivative, which does have a denominator, right? W squared. This is my first derivative. So it has a denominator. W squared equals 0. So W squared equals 0 at W equals 0. But when W is 0, then you're not getting a pen for the farmer. And so there's no pen here. And so that's certainly not going to be a value that gives us a pin, right? So that's because that's what we're looking at having as a pin. And that's 8,000 square feet of land. And so that would be no pin. And so wouldn't be enclosing the 8,000 square feet. Now I want to prove that this is a minimum on the cost. And then I'll find what dimensions. And so because that's what it's asking for. Now it could ask how much does it cost, but it didn't. It asked what are the dimensions again. And so I want to prove right over here, verify, we'll call it, that this is a minimum. And I like to use the second derivative test for this. It works out kind of cutely. So here was the first derivative. So if I take the second derivative, the derivative of this is 0. And then the derivative of this is going to be a negative times a negative is a positive. So this is C double prime equals, and then 2 times 16, which will be 32 with 4 zeros, right? So a negative times a negative is a positive. 32 with 4 zeros, W to the negative 3. And then I was saying that my maximum came at 40 square roots of 30, minimum, at 40 square roots of 30 over 3. So I'm going to put that in right here. And so maybe I would be happier if I had 32,000 four zeros over W cubed. But remember that I only care when I plug this in whether it's positive or negative. So I am going to go ahead and plug it in so that you know that that's what you do is you plug in this value, 40 square roots of 30 over 3 cubed. And all I care about this is it positive or is it negative? I guess, or is it 0? And because this is a positive value being cubed and divided by a positive value, this is positive, right? And so since this is positive, that means that at this critical value, it's concave up. So I'm going to draw something that looks concave up. So here's concave up, right? Because it was positive. Second derivative tells me concavity at this critical value. And so it's a minimum. It is a minimum. And so now I'm ready to find what L is. And so L is, and I'm just using the equation that I have there, 8,000 divided by W, right? Right here, L, 8,000 divided by W. And W is 40 square roots of 30 over 3. So I'm just going to put that in my calculator. So this is going to be, and in fact, I'm going to put in my choice. I'm cold, hungry, tired, grumpy. I'm going to put that value in, which is my W. And then I'm going to do 8,000 divided by the answer. I just think that will be easier to put in my calculator. So I'm getting 20 square roots of 30, which is approximately, 20 square roots of 30. I erased it on accident, which is approximately 109.5. I said I was going to go to the 10th feet. So the dimensions here are 40 square roots of 30 over 3 feet by 20 square roots of 30 feet. That's the exact value. And then I also have these approximate values here too, or 73 feet by 109.5 feet. My dad is always building stuff, and he's always asking me, I want this, I want my fence. I want my fence to be going, and I want a curve along here on the top, and I got to set my blade at a certain angle to cut this curve out so that he gets this fence with these boards that's going to curve like this. That's what he's wanting, or whatever have you. What angle am I going to set my saw at to cut this out like the way I'm wanting it, and how long are these boards are all going to be. And I give him answers like this, and he says to me, I want answers like this. That's what he says. Anyway, I think it's funny. Okay, because I'm a math person. Okay, and then this is a story that you can read if you want about Kepler. And that's it. This video is a wrap. Hopefully it even recorded.